So I made this set of 3 problems to kind of explore what it means to be an x-intercept, a vertical asymptote, or a hole in the graph. So if you want to pause and write these 3 options or these 3 functions down, then unpause it and we'll talk about it. So for this one, and in each of these, you see a lone x plus 2 in the numerator. And whenever a factor is in the numerator and only the numerator, that is an x-intercept. That's because that's when the function equals 0, right? So if I plug in -2, I get 0 divided by -6. I get 0 divided by 36, and then I get 0 divided by -6. So either way, I get 0, yeah? When the y value is 0 when x equals -2. So that's just an x-intercept. So each of these have an x-intercept at -2, not a big deal. We don't need to really talk about it. So the big question is what's happening at 4, right? So right here, at x equals 4, there is a single factor x minus 4 in the numerator and a single factor x minus 4 in the denominator. That means there is a hole in the graph. Because they simplify with each other down to just 1, this really just leaves me with y equals x plus 2 with a hole in the graph at 4. Well, and then the question is, at 4 what? Because the hole in the graph is an x-coordinate and a y-coordinate, true? And so you plug 4 back into the original, what it would be if that wasn't there, and you get 4 plus 2, you get 6. Which means this function might as well just be the graph. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. Okay. This might as well just be the function x plus 2, but with a hole in the graph at 4, 6. That was supposed to be an open dot. And so if you were to graph this in the calculator, then that's what you would get. Okay. In this situation, let's talk about this. We have a common factor in the numerator, another in the denominator, and then another in the denominator. So here's the thing. If these simplify each other out, and you're thinking hole in the graph, but then you're left with this, well, this right here means vertical asymptote. And the vertical asymptote is way more powerful than a hole in the graph. The vertical asymptote takes over as being the discontinuity. Okay, so if there are more factors in the denominator than the numerator, it is a vertical asymptote. Okay, and then in this one, the vertical asymptote at x equals 4. Okay, on this last one, we have a common factor in the top, we have a common factor in the bottom. Okay, so if we simplify those out, then I'm thinking hole in the graph, right? What I'm left with is x plus 2 times x minus 4. So I know, I'm thinking hole in the graph at 4 what though? So if you plug 4 into what's left over, you get 6 times 0. So what this means is that you just have a hole on the x-axis, right? If I had the function x plus 2 times x minus 4 over x plus 6, I would consider 4 to be sorry, you couldn't even see that, an x-intercept, because that's when the numerator and only the numerator equals 0. Well, it's kind of like, well, the numerator equals 0. I mean, there is no denominator other than a 1 anymore, but fact of the matter is that these were still there. At 4, the original expression does not exist. So it's just a hole on the x-axis. It's not an x-intercept. It's the quadratic that crosses at -2 and would cross at 4, except it's got a hole in the graph, so it does something like this. That's a terrible quadratic, but who knows what it is. Cool? Alright, interesting. Y'all said yes. Alright, so now what I'd like you to do is to think about these with me. If you want to pause and write all of them down and give yourself some space, then go ahead. Or we can just do it one at a time. So right here, in the numerator, I've got x plus 1, which means x equals -1 is something, and I'm pretty sure that means we have an x-intercept at -1, 0, because if I plug in -1, I get 0 in the top, and I get -4 cubed, so -64 in the denominator. But that is just a single factor in the numerator, that's an x-intercept. Now x minus 3, if I simplify out an x minus 3 with one of these down here, I'm left with 2 in the denominator, right? Which means I have more factors in the denominator, which means vertical asymptote, at x equals 3. Now, I have this right here, behavior, right? So what I like to say is, remember you've got two options when you have a vertical asymptote. They can be going to opposite infinities on either side. So this one's going up to positive and this one's going down to negative. Or they can be going to the same infinity on both sides, both positive. So in order to describe this, I kind of changed my mind on how I wanted to say it last year. I think last year I said something about sine. Then just say, for vertical asymptote, you can just say same infinity or opposite infinity. And in fact, because this now has a power of 2, that's a multiplicity of 2, that's an even multiplicity, then we'll say same infinity. Now that could be both positive infinity or both negative infinity. I don't know that. I'm just saying that they're both the same infinity, whichever one they are. Okay, well, let's talk about this. Add, or for this one, I see that I've got x plus 1 in the numerator and x plus 1 in the denominator. And it's the same amount on top and bottom, so that is a hole in the graph. And if I want to, I'm going to go ahead and simplify it before I find where the hole is. I'm going to simplify out one of the x minus 3's. Okay, so I'm left with just 1 over x minus 3 cubed. So if I want to find where the hole is, it's at negative 1, because that's the factor of that. And then I plug it into what's left over. 1 divided by, and then negative 1 minus 3 is negative 4. Negative 4 cubed is negative 64, so negative 1/64. Okay. Now, what is happening at x equals 3? You got a question right quick? Okay. Hey, I'm going to mute for 1 second, okay? Okay. And so, at x equals 3, we've got no more in the numerator, and we had more left over in the denominator, so that is still a vertical asymptote, just like this one. But because it has an odd multiplicity, we'll consider those to be opposite infinities. So if one went up to positive infinity, then the other one went down to negative infinity. I hope that y'all could see these earlier when I was drawing. I don't even know. Okay, so for this one, let's see. We've got x plus 1 quantity squared in the numerator, no more x plus 1's anywhere else. So to me, that means I have an x-intercept at negative 1, 0, and then because it has a multiplicity of 2, that means it's going to bounce. So if I were graphing this and I had an x-intercept here, whatever the rational function ends up looking like, and in fact there's higher power on the top, so it's kind of a slant asymptote, it could do something like this. Bounce off it, you know what I mean? So bounce off that x-intercept. Now let's talk about x minus 3. Okay, so there's 2 of them up here, 2 of them down here, leaving me with only 1 down here. And so with only 1 more left over in the denominator, we definitely have a vertical asymptote at x equals 3. That's an odd multiplicity, so the two sides go to opposite infinities. Opposite infinities. So let's talk about this one. X plus 1, right? So this ends up being very similar to this right here, except for because one of them cancels out or simplifies out from numerator and denominator, it still means that there's a hole in the graph, right? Because, so what I see is vertical asymptote trumps a hole in the graph because it's not more undefined, but it impacts the graph past just a hole in the graph, right? But if it's undefined, if it's in the denominator, it's either a vertical asymptote or a hole, right? So it can't just be an x-intercept. In this case, I still have a hole in the graph because there's more of them in the top. It just means I have an x-intercept, or sorry, I have a hole in the graph on the x-axis, right? So I have a hole at negative 1 something. Let's see, I'm going to go ahead and cancel out an x minus 3's or simplify out. So what I'm left with, essentially, is the function x plus 1 quantity squared times x minus 3 quantity cubed, even though that's not like the end. Oh, I don't need that. If I plug in negative 1, I get 0. Duh. So I have a hole at negative 1, 0. So if I plug in negative 1, I get 0. And then the denominators both simplified out. But it has a multiplicity of 2 on the x-axis. Yeah? So it's on the x-axis, there's a hole, and it bounces. So you got a lot going on right there. So if you can simplify it out, if it's in the denominator first off, if it's a factor in the denominator, it's either a vertical asymptote or a hole. It's not a vertical asymptote because there's not more left in the denominator, so it's a hole in the graph. But because there's more left in the numerator, it becomes an x-intercept, right? Not quite, but it's on the x-axis, the hole is. So then it's, because the multiplicity was 2, it would even bounce off that. So we're talking about something that looks like this, only instead of this being a closed circle, it would be an open circle. Now let's talk about 3. At x equals 3, it looks like we have another hole in the graph. At 3, and then again when I plug in 3 I get 0. So this would be on the x-axis. On the x-axis. But because the multiplicity left over is odd, then it would cross. Not through, but over the x-axis. Okay, I hope that kind of makes sense. It requires your memory of our talk about multiplicities and whatnot. Just recognizing what's happening to the function. So the next thing we're going to do is we're going to analyze and graph a couple functions, or 3 functions. I'm going to do one on this video, and then I'm going to stop the video and start the next one and do 2 more graphs, and we'll be done. So I'm going to draw an x and a y. I'm going to go 5 out on each should be fine. 1, 2, 3, 4, 5. Okay. I guess let's go ahead and list out all those things that we need to think about. Domain, x-intercept, y-intercept, vertical asymptote, hole, in behavior slash marginal asymptote, limits. So limit as x approaches negative infinity, and limit as x approaches positive infinity. Okay. So let's look at this. I am actually going to go ahead and expand this out just so we can have it. The numerator is going to be x squared plus x minus 2, and the denominator x squared minus 6x plus 9 times x minus 1. It's going to be x cubed minus x squared minus 6x squared, so minus 7x squared minus 6x, or sorry, plus 6x plus 9x is plus 15x, and then minus 9. Okay, so that is the expanded form of this one. I'll go ahead and write that down. Not that you need it, because we should be able to figure this out without, but sometimes it's kind of nice. Alright, domain. Domain is everything but, everything, or all the x values for which the function exists, and the function does not exist at 3 and 1. So negative infinity to 1, 1 to 3, and 3 to infinity. Okay? Before I get into all that, I'm just going to start going by, like, what do I notice? I notice that there's an x minus 1 and an x minus 1 on the top and the bottom, right? In the numerator and denominator. So there's the same amount, which means that there's a hole in the graph at x equals 1, comma, okay, well, what's left over? Because that's what I got to plug 1 back into, right? So if I plug in 1 to the numerator, I get 3, and if I plug in 1 to the denominator, I get negative 2 squared, so 4, so what, 3/4? So I have a hole in the graph at 1 and 3/4. Okay. So that takes care of that. Let's talk about the numerator, x plus 2. So having a factor of just x plus 2 in the numerator means x-intercept, because that's if I plug in negative 2, I get 0 divided by negative 5 squared. Right. So x-intercept would be at negative 2 comma 0. So I know I'm crossing at negative 2, 0. Well, I don't know if yeah, I do know I'm crossing because the behavior was multiplicity of 1, true? X minus 3 quantity squared in the denominator. Okay, so that's in the denominator only. That means, or more times the numerator. That's a vertical asymptote. The fact that it has an even multiplicity means same infinity as far as the behavior around it, right? So x equals 3. They're either both up or both down on either side. Okay? So we've got that. And let's go ahead and answer that once we finish this. The vertical asymptote is at 3, so we're going to say as x approaches 3 from the left, and as x approaches 3 from the right. So don't forget that superscript of minus and plus means from the left, and this means from the right. Okay? And then let's talk y-intercept. Y-intercept is when x equals 0. So x equals 0 is not claimed as a vertical asymptote or a hole or an x-intercept, so we're just going to plug in x equals 0. You can plug it in here. 0 plus 2 times 0 minus 1, although these can just simplify out. So 0 plus 2 over 0 minus 3 quantity squared, which is going to be 2 over 9. Or you can just look at the expanded form and then just do negative 2 divided by negative 9 because all the x's are 0 when you're trying to find the y-intercept. And that's 2/9. So 0, 2/9. So 2/9 is like 0.2 repeating, so somewhere in there. And then in behavior, so as far as in behavior goes, what you want to do is think about your powers. When I look at this, the higher power is in the denominator. If the higher power is in the denominator, then that means it is automatically a horizontal asymptote at y equals 0. Okay? If the higher power is in the denominator, if you simplify that, x squared divided by x cubed might as well just be 1 over x. So you start, x starts getting larger, 10, 100, 1,000, a million. 1 divided by that is an increasingly small number. Okay, so I have a horizontal asymptote here. Now, that being said, I know that a horizontal asymptote models the end behavior. It doesn't necessarily tell me what's happening on the interior, because you can tell I do hit and cross the x-axis, right? Multiplicity of 1. Well, that's okay. It's just kind of weird. What I do know is that this is this is telling me a story. It's saying, hey, go from here and then up a little bit and then up a little bit more. This is telling me to go up. I know I don't go down because I have to go through this point into the hole in the graph. I don't have another x-intercept, so I have to go up. So this is going to be through here, hit that but don't go through it, and then come up and then there you go, right? Now, this means right here it goes through the x-axis and then dips down below and then comes back up. I don't know exactly where it reaches its minimum right there, but it does do something like that. Okay? So it will come through, dip below, and then come back up. And I know it doesn't cross the x-axis again. There's no more x-intercepts. So that has to just come from below and go towards it. Now, this right here is kind of, I mean, like there's nothing really to go on. There's no x-intercepts. There's no holes in the graph on this side of 3 except for one thing. My vertical asymptote had a multiplicity of 2, which means it has to come from the same infinity, which tells me that I'm up there. And now I have my graph. Okay? So 2 answers I can answer right away, or the last 4 things I need to answer. As I go to the infinities, the function is leveling off to 0. So whatever the horizontal asymptote is, that's the same thing as that. And because they had the same infinity, and this side went up to positive infinity, so does this side. As you approach 3 from the right, you're going up. As you approach 3 from the left, you're going up. And there we go. Okay, I'm going to stop the video and then graph the other 2 in the last video.